For this tutorial, we'll be building off of what we made in structures.cpp. The arrays.cpp source file contains the modified code. The definitions of the student and book structures and functions remain the same, so you needn't look at them. Just skip to the main function. An easy way to remove particular parts of your code in Visual Studio is to collapse program modules by clicking the minus icon in their block. To expand again, you can click on the plus. Imagine we need to calculate the GPA of a student in one term. We'll need a series of variables, one for each course. That's 5 lines. 5 variable declarations. We can condense this to one line by declaring them all at once, but that might not be of much help. Let's say our program has tens, hundreds, or even thousands of items to work with. Even the GPA of a single student over the course of their program would involve 40 grades. And what if you have a mere 5 students? That's 200 grades. Declaring these grades as variables individually just isn't going to work here. Maybe you're thinking about using structures here. Well, unfortunately, that just moves the problem from the main function to your structure definition. Sure, you don't need to declare 200 grades, you just need to declare 40 of them at once and then start declaring students in main, but that doesn't really fix the problem. Instead, we need to declare a whole bunch of effectively identical variables at once. The way we do this is with arrays. An array is something like a list. You add a pair of square brackets to the variable name, and within those brackets, you put a number. You now have that many variables. So if we want 40 grades, we just write int grades and in square brackets, 40. Like magic, we have 40 grades. Each of these grades can be accessed individually by referring to their index in the brackets. The index is their place in the list. Indices start at 0 and go up to the number of elements in the array minus 1. This fact trips up a lot of new programmers, so be sure to keep that in mind. With 40 elements in the array, our indices go from 0 to 39. Arrays are really useful and can be found in almost all programming languages. So, how do arrays differ from structures? Well, the difference is in their data type. Arrays are used when you need a lot of just one thing. 40 ints, 40 floats, or what have you. Structures are used when you're working with a lot of different but related data. If your data is of mixed types, then you use a structure. And incidentally, you can happily use both. You can have arrays of structures or structures with other member structures or member arrays. So we can access each element just like a normal variable. The index is effectively a part of the name, in a similar way to structures being a part of their members' names. So you can initialize the elements in the array by writing the name of the array and their index. But you might notice a problem here. We've avoided creating 40 variables in one go, but we still need to initialize them. As it happens though, the best thing about arrays is that they work really well with for loops. We can write a loop that goes through all the members of the array by using the loop counter, I, as the index value. The loop starts with I equals 0, and the condition will be I less than the number of elements. Then we just initialize one of these variables once, and instead of using a hard-coded index, we use I. Now we have only a couple of lines of code that initialize the whole set of elements. Easy. Bear in mind that if the array size increases, any loops that handle the array in this fashion need to be adjusted too. This can be made much easier by defining a label at the top of the program. The label will define the number of elements and can be used in that number's place throughout the program. This is done by writing #define data size 10. Notice the differences between this and the rest of the code. There's no equal sign and no semicolon. That's because this isn't exactly normal C. This is what's called a Preprocessor Directive. Basically, it's a command that gets executed before the program gets compiled. All this does is replace every instance of data size throughout our code with the number 10. It's not a variable, so it can't be altered. What it can do is act as a constant value in our program. Wherever it's used, the value it refers to is 10. Actually, the fact it's not a variable is important. If you tried to use a variable to define the size of an array, your compiler would complain quite a bit. The program must know the size of an array when it gets compiled, so variables aren't allowed since they can change at runtime. Anyway, if you look at the sample code, you'll see an example of randomizing the initial values of the grades and calculating the average. We've seen this code before, but now it's using arrays to handle a larger number of variables. And notice how we use data size here instead of a hard-coded number? Without it, we'd need to manually change the number every time we adjust the array size. And again, remember that for every new piece of information, we create a variable for it, including sum and average. Have a look at the sample code for finding the maximum value in the array of random numbers. This code lives in the main function and currently only works with a particular array of a particular size. As we saw in the C functions tutorial a while ago, we can create a function to repeat the same operation for different data multiple times and at different parts of our program. Arrays, as it happens, can be passed into a function just like any other parameter. If we want the function to work with any array of any size, we also need to specify the length of the array. This is so the function knows how much data it's working with. Take a peek at the workings of the function in the sample code to see how it manages that. You can also see min and search for more examples of using arrays in functions. As we mentioned earlier, you can happily use arrays and structures together. For an example of this, we can look at the school function in the sample code. This function emulates a school system and demonstrates how to define an array of variables that are based on a structure. Every variable that has square brackets at the end of its name is an array, so in this example, BIT 2017 is not a single variable, but an array of them. All elements of an array have the same type as the one specified at its declaration. So again, in the example, every member of BIT 2017 is a student. Once we know the name and type of an array, we can use each member just like any variable of that type. So any member of BIT 2017 will have its own ID, age, and so forth. Now let's think about the library function. It uses the book structure to simulate a simple library system. We create an array of book variables first and then use the getBookInfo function to initialize them. We then stay in a loop that displays a menu of options for the user in each iteration. The options are printing a book's info, borrowing a book, returning a book, and ending the program. Notice how this is in its own function? Remember, you should always create modules of code to simplify your program and allow reuse. Once the user has made a choice, we perform the action. Again, we've made smaller functions to perform each of these three actions. These functions receive the array and its size as parameters, much like the previous examples. We have library report, which is a simple loop that calls printBookInfo for all the members of the array. Library borrow and library return first ask for a book ID and then check to see if this ID exists. To search for an ID, we made a new function called library search. This function loops through the array and checks each index of our book array for a given ID, and returns the index of the book once the function finds it. Otherwise, it returns -1, indicating the book was not found. If the ID does exist, then we can call the borrowBook or returnBook functions, based on which action the user wants. Alright, that's the end of this video. We'll see you in the next one.